Hi there, welcome to your lesson on variance and standard deviation. Fantastic topic, I'm excited. Let's get started. Not too long ago, we talked about the measures of central tendency. These are the statistical measures that tell us about the center of a data set, and they are mean, median, and mode. Now we have shifted into measures of dispersion. To disperse means to spread out. So therefore, our statistical measures of dispersion tell us about the spread of a data set. We know range is a very simple measure of dispersion. It is just highest value minus lowest value. It's the range, the full range of values we have. Interquartile range was another type of range which we found by subtracting the third quartile and the first quartile values. We also mentioned, and now we're coming back to it, standard deviation. This is also a very common and powerful measure of dispersion, and that's what this lesson's all about. Let's get rolling. Okay, standard deviation and variance. To deviate just means how far are you from the normal. So standard deviation means how far are we away from the mean. Let's take a look at this through an example. So standard deviation is a measure of how spread out numbers are. Our example is this. We have some dogs, and you have measured the heights of these dogs to their shoulders. So you can see it's marked with these red things here. That's the height of each of these dogs to its shoulders. And here are the values we have. 600 millimeters for this dog, 470, 170, 430, 300. Okay, those are the heights we collected. Now, what is the green line? Well, the green line is the mean. If we calculated the mean of all these, the average, we would get 394. So that's the average height of the dogs we see. Okay, so now standard deviation tells us how far away we are from the mean. So what we're going to do is, here's our data values again, here's the mean, and we're checking how far each data value is from the mean. You can see this one is 206 from the mean, 76 from the mean, 36, negative 224, and negative 94. So the distance from the mean. Okay, so to find the variance, which is how we begin here, to find standard deviation, we begin with the variance. We take all our distances from the mean and we square them. So you can see all the values have been squared here. And then we divide by 5. So we're adding the values, the square of the values, and dividing by 5. So it's kind of like we're finding the average. We're finding the average distance from the mean of the data points, the average distance from the mean. And we're squaring it too, and that's important. We'll take a look at that y in just a second. So you square those, you divide by 5, and you get this large number. So the variance is always going to be a big number, well, depending on your data set, but it'll be a big number definitely compared to your standard deviation. Because this is not really the average, right? If we've squared these, this is currently the average of the squares. So how do we undo that squaring? Well, we can just, to find the standard deviation, it is shown by this symbol, we just take the square root of the variance. And in a way that's undoing all these squares, but not really. If you know how square roots work, you can't just take a square root of this side and then square root of this side to undo all these squares. So it's a little strange what's happening here mathematically, but you should know in general that number we get, the standard deviation, is a measure on average how far we are from the mean. Okay, so in general here we are 147 centimeters or millimeters from the mean. Okay, so variance and standard deviation. Again, I need to point this out again. We're squaring the values, the distances from the mean, and then taking a square root at the end to take us back to standard deviation. Okay, let's take that a little bit forward. So that's what we did here. Now let's talk about some things. So why are we squaring the differences? Why didn't we just find the distances and take the average, right? If our goal is to find out on average how far we are from the mean, why didn't we just add them up and divide by 5? Well, here's an example of why we don't do that. If we don't square, for example, if a data point was 4 away from the mean and 4, and another one was -4, -4, just like here we had positive away and negative away. What would happen if you average these? Well, you add them up, divide by 4, you get 0. So the result, if you just added those, is 0. It's telling you like the data does not deviate from the mean at all, but we clearly see the data does deviate from the mean. So those positives and negatives cancel each other out, and that's what would have happened in our data set. If we didn't square them, we would have had positive values and negative, and the negatives would kind of cancel part of the positives, and it wouldn't show us an accurate deviation from the mean. So the squaring gets rid of the negative integers. That's the purpose of the squaring. Okay, so a natural question by students who are really thinking about this is like, well, squaring, why are we squaring them? Why don't we just take the absolute value? Because an absolute value also gets rid of negative values, right? That's what an absolute value does. It keeps positive numbers positive and it turns negative numbers positive. So couldn't we have just applied an absolute value and then taken the average like that? Sure, okay, so 4, 4, negative 4, negative 4. Okay, 4, 4, negative 4. Those turn positive, so you end up with all positives, divide by 4, 4. Okay, what's wrong with that? That shows us on average we are 4 away from the mean, and that's clearly what's happening. We are on average 4 away from the mean positive direction, 4 away in the negative direction. So isn't this more accurate? Isn't that fine? Can't we do that? Why square it? Okay, let's take a look further. So here's what we just tried with absolute values. Let's look at this example. Let's say we had this data here. We were 7 away, 1 away, then 6 below, 2 below. Okay, let's apply this new absolute value technique we're talking about. So absolute values, okay, turn those values positive, and then find the average. So now it says, on average, this data set is also on average 4 away from the mean. So hold on a second. This data is on average 4 away from the mean, and this data is also on average 4 away from the mean? Well, it might be, truly, yeah, but numerically, yes, these are on average 4 away, but that 4 doesn't really tell you the true story of what's happening here, because this data is very different than this. Here, they are certainly always 4 away from the mean, but here, sometimes they're further, sometimes less. Like that 4 doesn't really capture that this data is different and that there's more variation going on here. So that's why we come back to squaring them. When we square them, it gets rid of the negative, but it also, what squaring does, it also exaggerates the effect of large numbers that vary a lot. For example, the 7, by squaring it, you're kind of exaggerating its effect, and that's fine. When we have these outliers, we want their effect to be shown as an exaggeration. We want to show there's more variance because we have these crazy outliers. So notice when we did the squaring and then the square root, which is our normal approach for standard deviation, for the data where they're all away by 4, we get the same value. We get 4, the same as we got when we did the absolute value approach. So that tells us on average those are 4 away. Great. This one, the absolute value technique gave us 4 also, but this data is very different. So now when we apply the squaring of the values in the square root, the standard approach for standard deviation, now we get an answer of 4.74. So absolute values produced 4 and 4, but now we have values of 4 and 4.74. And this is better. This tells us that this data has more variance. It has a different kind of variation from the mean than this does, and that's absolutely true. So that number is a better indication of what's going on. It's an exaggerated average, which is what we need here. Okay, with that, let's keep going. And now we're back at our doggy example. So we have our dogs, and we found the standard deviation from the mean is 147 for these dogs. Okay, let's show that on the graph here. So here's the standard deviation highlighted on there. 147 above, 147 below the mean. So you can see most of the dogs' heights are within that one standard deviation, except for this dog. That dog's height is more than one standard deviation below the mean, and this dog's height is more than one standard deviation above the mean. Okay, but these other dogs fall within one standard deviation of the mean. All right, let's take it a little bit further. Here is what's called a normal distribution, and things like heights and weights and things like that are usually distributed normally. That means there's a mean. This symbol here means mean. So there's a mean value. And imagine that this, instead of a curve, is a histogram. Okay, so a bunch of bars. You could see most of the data is here. This would be the highest bar in your histogram. Most of the data is around the mean, and lots of data around the mean. And then as you go further from the mean in each direction, there's less and less data further and further. So in other words, this is kind of like outlier data, so there's less of it, less of it. Most of the data is clustered around the mean. Now, the standard normal distribution has some interesting properties. First of all, if you go one standard deviation from the mean, so one down or one above, that you can see is 34 plus 34. About 68% of the data is within one standard deviation of the mean. So back in our dog example, we can apply that as well, but let's show that here. So again, within one standard deviation of the mean, 68% of the data lies within one standard deviation of the mean. So for our dog example, same thing. Here's one standard deviation from the mean, positive and negative. Therefore, 68% of the data lies there. Of course, this is a small sample. It's only 5 dogs. But imagine this was a sample of 100 different dogs and you still had the same data, let's say. Well, you could say 68% of the dogs are within one standard deviation of the mean. So that means this tall dog and this little one are in that 32% group that is outside, like further away. So they're kind of like outliers, but are they really outliers by our definition of an outlier? If you are within a 32% minority group, is that really an outlier? I don't think so. So here's how we calculated outliers before. We would do 1.5 times IQR, and we would subtract that from quartile 1 value and add that to quartile 3 value. And that would give us this range of values that are considered acceptable, and anything beyond that range of values is an outlier, right? Let's see how that goes onto our normal distribution curve. If we applied the 1.5 times IQR rule, we would end up being here on that positive side. So this would be like 1.5 times IQR plus Q3. You'd end up here, which is mean plus 2.7 standard deviations. So now you're not only just one standard deviation away, not two, you're 2.7 standard deviations. And guess what? What percentage of data is here beyond that point? Only 0.35% of data lies here. Okay, let's go on the negative side. If you did Q1 minus 1.5 times IQR, you would end up right here in the data set. And that is also negative 2.7 standard deviations from the mean. So notice most of the data then is here, right? All like 68% plus another 27 it looks like, which is about 95 plus more. And again, we're left with only 0.35%. So in total, that's 0.35 plus 0.35. So there's only 0.7, less than 1% of the data lies outside of this range that we create by doing this IQR calculation. So if you lie outside of that, there's such a small chance that you're part of a very tiny group. Again, 0.7%, less than 1% of data is there. So of course it's an outlier. That's why this calculation is used to show outliers, because if you are in that zone here or here, you're definitely way beyond the bulk of the data. You are an outlier for sure. So essentially, if you use a multiplier of 1.5, this will ensure that for normally distributed data, our range of allowed values captures 99.3%. So again, 99.3% of the data is here. That remaining 0.7% is so far from the mean that it is considered outlier data. Okay, I hope that brings that idea to life for you. Let's keep going. Let's go back to our example of students who took a test, and here are their test scores. They can score 0 to 10. Okay, we've already broken this data up, but let's take a look one more time. I took the data, I put it in order, and I split it up into 4 parts, which is our 4 quartiles, right? So our median Q2 value is here. Our Q1 value would be here. Our Q3, quartile 3 value would be here. Okay, we talked about measures of central tendency. So, of course, median was one of the measures of central tendency, and here it's 5.5. Our mean, if you calculate the mean for this data, is 5.25. And of course there's mode, but I don't have mode here. Okay, now we're talking about measures of dispersion. One easy measure of dispersion was the range, right? If you look at from minimum to maximum, the range in this case is 10. Okay, another measure of dispersion, the IQR, right? The distance between Q1 and Q3. In this case, it's 3.5. And now we're talking about standard deviation. So here's a little portion of our data. I took this middle portion here just to highlight something about standard deviation. We have been talking about standard deviation with the dog example. Okay, and in the dog example, we broke down how the process of finding variance first, right? Here's the formula. We are taking each data value, we're subtracting the mean, because again, remember, we're seeing how far it is from the mean. So that will tell us how far we are from the mean. And then you square that. We talked about that, why we square it, okay? So subtract the data value, subtract the mean, see how far it is, square it, and then do the sum of that. So you're going to repeat that for every data point. Sum, okay? And then at the end, you divide by the number of data points. So again, it's like an average of the distances from the mean, right? So then that we took a step further and said, okay, variance is going to give us that big number, and then we have to take a square root at the end to undo all this squaring that we did, right? So we take a square root of all that and we get our standard deviation. So for this example, let's say we took this data point right here. We would do 5 minus 5.25 to check how far it is from the mean, square it. Okay, let's take another data point. Let's say this one. We would do 7 minus 5.25 To find the distance, square it. Okay, so it's kind of like an average of the distances. If you went through that process further, okay, so we just saw the calculation of the difference from the mean for 2 of the points. But to find the variance, we need to do that for all the points, right? We need the sum of all those differences squared. So let's see that on the next slide here. Here's our data again with the mean. Here is all the data points. Okay, so first data point, 0 minus the mean, negative 5.25 squared. Okay, next one, 1 minus the mean, negative 4.25 squared, on and on and on. Every data point, subtracting the mean, squaring it. So there's all those. Then you take, to find the variance, right, we take the sum of all those. So in this case, if you sum up all those squared differences that we see here, you get 198. And we have 32 data points, so we divide by 32, we get 6.19. Notice that's labeled as standard deviation squared, which is our variance. So that's our variance number. And like I told you, the variance is always going to be higher than the standard deviation because it's the square, right? So now we take the square root of that to find the standard deviation. Square root of the variance in this case is 2.49. So what that means again is by taking the square root, we've undone all that squaring that we've done here. And it tells us in general, kind of as an average distance from the mean, the scores of these students on this test are on average 2.49 away from the mean. And again, this is a slightly exaggerated average because of the squaring that occurred in the beginning. All right, so that is standard deviation. We call this here, sigma, the population standard deviation, the standard deviation for our full data set. And here is our variance, population variance. So those are two formulas. And you should know that in general, we do not use that formula. You may want to use that formula and show the steps like we're shown here, if you're working on your IA, for example, just to show your understanding of the formula. But in general, in terms of just exams, we do not use that formula. Okay, the expectation is that you use your GDC and it will calculate this for you. So on your GDC, okay, so let me just remind you how to do that. Here's the calculator. You will press stat. Then you'll go to number 1, edit. That's where you enter your data. I've already pre-entered some data in list 1, so you can enter some data there. This is random data. It's not the data we just saw. Now you will go to stat again and press the arrow over to get to calc and select number 1 variable stats. We've used that before to find mean and median and so on, but now we're going to use it to find standard deviation as well. So list 1 is the list we're gathering data from, and we're going to hit calculate. When I run that, I can see my mean is 8, and I can see my standard deviation right here, 2.82. So again, each value minus the mean, square it, another value minus the mean squared, I'll divide by the number of, that gives you that value there, right? Everything we've shown in this video is calculated there for you. So some properties of standard deviation. First of all, standard deviation is only used to measure spread or dispersion around the mean of a data set. Variance, and therefore standard deviation, is never negative because it is an average of the squared distances, right? So always be a positive value. Standard deviation is sensitive to outliers. Like I said, since we're squaring the values when we're doing the difference from the mean, we are exaggerating the effect of those numbers that are far away from the mean. So a single outlier can raise the standard deviation and in turn distort the picture of spread. And for data with approximately the same mean, the greater the spread, the greater the standard deviation. So we can see here, these two data sets have the same mean, but one is more spread out, one is less spread out. Therefore, low standard deviation, high standard deviation. Okay. Question, why do we have standard deviation and variance? Why is there these two measures? Why not just have one? The reason is, well, first of all, you don't really need both, right? They each have different purposes. The standard deviation is usually more useful to describe the variability of the data, while the variance is usually used much more in different mathematics. When you do a lot of higher level statistics, you'll notice the variance is a more important measure when calculating many things. Okay, so let's do some practice now. So here is our first calculator practice problem. Let's say we have the world's top 10 athletes earnings in millions of dollars in year 2017. So we can see here, Cristiano Ronaldo earned 93 million US dollars. And then the next, LeBron James, 86.2, and on and on. Okay, so your job is to find the standard deviation. Try it now. Okay, you've entered that into your edit menu, into list 1. You found the standard deviation, and you found it to be this, 16.9. Here it shows the full formulas and calculations, but of course you can rely on your calculator, and you got this value for mean and this value for standard deviation. Check your work. Okay, next one, let's try again, another one here. Here we have Hans car dealership, and it has 25 cars for sale. The prices are in thousands of yen. Okay, so we can see 3 cars are priced like this, 6 cars are priced like this, 11 like this, and so on. So remember, this is now a frequency table, and we are shown how many data points lie in each of these ranges. So remember, when you enter this into your calculator, you should enter these as a mid value. So what's the value right between 100 and 200? Well, 150 would be in the middle. And what would be the mid-interval value here? 250 and so on. So enter those values, then enter these into your list 2 as a frequency list. And then when you calculate your one variable statistics, make sure you have list 1 for your data and list 2 for your frequency list. So let me show you that. If I go to stat, calc, one variable stats, list. So if you've entered this as 2 lists, again, here, you would enter list 1 here, then you go for frequency list, you'd have to go second and then 2 for list 2. All right, then it will know that it has to multiply each of those values by 3 and then 6 and 11 and so on. Calculate, and it should give you that. Let's check. For this one, our mean was 322. Our standard deviation was 91.7. Check your work carefully. And third one to try through calculator is this one here. A real estate agent recorded the number of rooms in the houses that she was selling. So here's the number of rooms, and here's how many houses have that many rooms. So this might be confusing, like what's our data here exactly? Well, the data is the number of rooms. So the houses here represents the frequency. Okay, so think of this one as your frequency list here. So 2 houses had 1 room, 2 houses had 2, and so on. So again, this is your frequency list. So find the mean and standard deviation, and then remove house 18 and find the new mean and standard deviation, because house 18, the house with 18 rooms, because that one is definitely an outlier, right? Every other house, 1 to 7 rooms, and then all of a sudden there's this crazy outlier here. So we're going to remove the outlier and see how much the mean and standard deviation change, because we know both the mean and standard deviation are really affected by outliers. So let's see just how dramatic that effect is. Let's check here. So for the full set, our mean is 4.63 and our standard deviation is 2.67. And then when you remove that outlier, we have a mean of 4.24 and a standard deviation of 1.4. So you can see that the mean dropped and the standard deviation dropped a lot, because again, standard deviation, we square all the differences, and that squaring there really exaggerated the effect of that outlier. So remove it, it changes dramatically. Okay, great job. You are now a master of standard deviation. We will see you soon.